Hello and welcome, fellow cosmic travelers. Look up into the night sky. In that vast, dark expanse, a phenomenon exists so extreme, so mind-bending, that it challenges our very understanding of reality. We're talking about black holes, regions of space where gravity becomes so powerful that nothing, not even light itself, can escape its grasp. These cosmic monsters warp space and time, devour entire stars, and hold the secrets to the fundamental nature of our universe. They are the ultimate paradox, destroyer and creator, death and rebirth, all written in the elegant language of Einstein's equations. For centuries, black holes were just ghosts in the machine, theoretical impossibilities lurking in mathematical formulas. But today we've not only proven they exist, we've photographed them. We've heard their cosmic collisions, and we've discovered they hide at the heart of nearly every galaxy. The story of black holes is our story, a story of pushing beyond what seems impossible to uncover truths, far stranger than any science fiction writer ever dared to imagine. So, what exactly defines one of these cosmic beasts? A black hole is a region of spacetime where the gravitational pull is so intense that the escape velocity, the speed needed to break free, is faster than the speed of light. At its very center lies the singularity, a point of infinite density where the laws of physics as we know them completely break down. Surrounding this is the event horizon, the point of no return. It's an invisible boundary marking where space-time curves so severely that all paths, all possibilities, lead only inward. The size of this boundary is called the Schwarzschild radius, first calculated by the brilliant German physicist Karl Schwarzschild back in 1916 while he was serving in the trenches of World War I. To really grasp how extreme this is, imagine this. For Earth to become a black hole, you'd need to compress our entire planet down to the size of a marble, just 9 millimeters across. The Sun would need to be squeezed into a ball only 3 kilometers in diameter. The density is simply beyond our comprehension. A single teaspoon of black hole material would weigh more than Mount Everest. This isn't just about squashing things, it's the very fabric of reality folding in on itself. The idea of black holes actually has a surprisingly long history, stretching back over 2 centuries. In 1783, an English clergyman and scientist named John Michell first proposed the existence of dark stars, bodies so massive that even light couldn't escape them. A few years later, in 1796, the French mathematician Pierre-Simon Laplace independently came to the same conclusion. But these ideas were largely forgotten because the physics of their time, Newtonian physics, couldn't properly describe such objects. The concept needed a revolution, and that revolution came in 1915 with Albert Einstein's general theory of relativity, which described gravity not as a force, but as the curvature of space-time itself. Within months of Einstein publishing his equations, Karl Schwarzschild found the first exact solution while fighting on the Russian front. Tragically, he died shortly after from a disease contracted in the war, never knowing his equations would one day prove to be prophetic. For decades, many physicists, including Einstein himself, believed these Schwarzschild singularities were just mathematical oddities, not real objects. It wasn't until the 1960s, thanks to the theoretical work of physicists like John Wheeler, who actually coined the term black hole in 1967, that the scientific community began to accept that these objects could and indeed must exist in our universe. Now, not all black holes are created equal. They come in several distinct categories based on their mass and how they form. First, we have stellar mass black holes. These are born from the deaths of massive stars at least 20 times the mass of our Sun. When they run out of fuel, they collapse in a catastrophic supernova explosion, leaving behind a black hole that's typically between 5 and 100 times the Sun's mass. At the other end of the scale are the supermassive black holes. These behemoths, containing millions or even billions of solar masses, lurk at the centers of most galaxies, including our very own Milky Way. And then there's the elusive middle child, intermediate mass black holes, ranging from hundreds to thousands of solar masses. How they form remains one of modern astronomy's greatest mysteries, but the family might be even bigger. Theoretical physics also predicts the existence of primordial black holes, tiny black holes that could have formed in the extreme conditions right after the Big Bang. These could range from microscopic masses up to several times the mass of the Sun. Some scientists even speculate they might be the answer to another cosmic mystery: dark matter, the strange substance making up 85% of our universe's mass. There's even a theoretical possibility of creating micro-black holes in particle accelerators. But don't worry, they would evaporate almost instantly through a process called Hawking radiation and pose absolutely no danger. So, why should we care about these cosmic vacuum cleaners? Well, black holes aren't just cosmic oddities. They are fundamental to how our universe works. Supermassive black holes act as galactic regulators, their powerful jets and radiation controlling the rate of star formation across billions of light years. They serve as natural laboratories, pushing the limits of Einstein's relativity and quantum mechanics. The collision of black holes creates gravitational waves, ripples in the fabric of spacetime itself, that carry information about the most violent events in the cosmos. Understanding black holes means understanding gravity, spacetime, the ultimate fate of matter, and maybe even the origin of our universe. In fact, recent discoveries suggest that black holes may have seeded the formation of the very first galaxies, acting as gravitational anchors around which matter could gather. They are cosmic recycling centers, processing stellar material and over unimaginable timescales, releasing it back into the universe as Hawking radiation. Some theories go even further, proposing that our entire universe might exist inside a black hole in a higher dimensional space, or that black holes could be gateways to other universes. These aren't just wild science fiction plots. They are serious scientific hypotheses being investigated by the world's top physicists right now. The 21st century has brought us revolutionary breakthroughs in actually seeing these invisible giants. In 2015, the LIGO Observatory made the first ever direct detection of gravitational waves, which came from two black holes colliding. This confirmed a century-old prediction from Einstein and opened a brand new window to the universe. Then, in 2019, the Event Horizon Telescope collaboration did the impossible. They released the first ever photograph of a black hole's event horizon. It was the supermassive black hole at the center of galaxy M87, 55 million light-years away. The image, showing a bright ring of light around a dark central shadow, was a stunning confirmation of decades of theoretical work. And the discoveries kept coming. In 2022, the Event Horizon Telescope team released an even more breathtaking image, the first photograph of Sagittarius A-G, the supermassive black hole at the heart of our own Milky Way galaxy. This incredible achievement required coordinating radio telescopes across the entire planet, effectively turning Earth itself into a giant telescope. Today, NASA's Chandra X-ray Observatory, the Hubble Space Telescope, and the new James Webb Space Telescope continue to find new black holes and reveal their secrets. We are truly living in a golden age of black hole astronomy, with new discoveries constantly reshaping our understanding of these incredible cosmic enigmas. To understand one of the most mysterious objects in the universe, the black hole, we first need to journey into the heart of a star. Stars are magnificent cosmic furnaces, gigantic balls of hot gas held together by their own gravity. Deep within their cores, a process called nuclear fusion is constantly at work. Hydrogen atoms are smashed together to create helium, releasing a phenomenal amount of energy. This energy pushes outward, creating a pressure that perfectly balances the inward crush of gravity. This delicate dance keeps the star stable in a phase astronomers call the main sequence. Our own sun has been in this stable phase for over 4.5 billion years, and it's got about another 5 billion to go. The core of our sun is an unimaginable 15 million degrees Celsius. It's so hot that hydrogen nuclei, which normally repel each other, are forced to fuse. Every single second, this process converts about 4 million tons of matter into pure energy, all according to Einstein's famous equation, E=mc². This energy creates a radiation pressure that prevents the star from collapsing under its own immense weight. It's this balance between gravity's pull and fusion's push that defines a star's entire life. And the key factor in that life story? Its mass. The more massive a star, the faster and hotter it burns, leading to a short but spectacular life of just millions of years. In contrast, small low-mass stars sip their fuel slowly, potentially living for trillions of years. Our sun is somewhere in the middle, but for a black hole to be born, we need to look at the true giants, stars more than 20 times the mass of our sun. Eventually, the fuel runs out. For a massive star, this is where the real drama begins. Once the hydrogen in the core is gone, gravity takes over, compressing the core until it gets hot and dense enough to start fusing the next element, helium. This creates carbon and oxygen. The star then develops a structure like a cosmic onion, with different elements fusing in concentric shells around the core. But each new fusion stage is a losing game. It releases less energy and happens much, much faster. Fusing helium might take 1,000,000 years, carbon just 1,000. And the final stage, silicon fusion, lasts for mere days. As the star ages, its core burns through progressively heavier elements, from hydrogen to helium, to carbon, neon, oxygen, silicon, and finally iron. The core temperature can soar to a staggering 3 billion degrees Celsius, 200 times hotter than the sun's core. Meanwhile, the star itself swells into a red supergiant. If a star like Betelgeuse replaced our sun, its outer edge would swallow all the inner planets, reaching past the orbit of Mars. But iron is the ultimate dead end. Fusing iron atoms doesn't release energy, it consumes it. Iron is the most stable element, the final ash of the nuclear fire. Once the core is made of iron, the star's fate is sealed. The iron core grows until it reaches a critical mass of about 1.4 times that of our sun, a limit calculated by the brilliant astrophysicist Subrahmanyan Chandrasekhar. Beyond this point, not even the quantum forces between electrons can hold back the relentless crush of gravity. When the iron core crosses that Chandrasekhar limit, the result is catastrophic and unbelievably fast. In less than a single second, a core the size of Earth collapses down to a sphere just 20 kilometers across. This is one of the most violent events imaginable. The collapse happens at nearly a quarter of the speed of light. Electrons are crushed into protons, forming neutrons, and the core's density becomes astronomical. A single sugar cube-sized piece would weigh as much as all of humanity combined. This implosion releases an insane amount of energy, about 100 times more than our sun will produce in its entire 10 billion year life, all in 1 second. Almost all of this energy floods out as a massive burst of ghostly particles called neutrinos. They stream through the star, carrying away enough energy to trigger what comes next. Believe it or not, our detectors on Earth can spot these neutrinos from nearby galactic events, giving us a heads up before the light from the explosion even reaches us. The collapse is so complex that it takes the world's most powerful supercomputers months to simulate just a few seconds of it. The core implodes until the nuclear forces that hold atoms together finally push back, causing it to bounce. This rebound sends a titanic shockwave blasting outward through the star's layers, ripping it apart in a spectacular supernova explosion. A supernova is an event of cosmic proportions. For a few weeks, that single dying star can outshine its entire galaxy of billions of other stars. The blast flings the star's outer layers into space at over 10% the speed of light. This cosmic debris is rich with heavy elements forged inside the star and during the explosion itself. The carbon in our bodies, the oxygen we breathe, the iron in our blood, every atom was created in the heart of a star and scattered across the galaxy by a supernova. We are quite literally made of stardust. The energy of a supernova is mind-boggling. It's 10,000 times more energy than you'd get if you could convert the entire Earth into pure energy. This is where the universe's heaviest elements are made. Every bit of gold, platinum, and uranium in existence was forged in the fiery chaos of a supernova or a collision between two neutron stars. The expanding gas from a supernova creates a beautiful, glowing nebula that can last for thousands of years, like the famous Crab Nebula. These remnants can even compress nearby gas clouds, triggering the formation of new stars and planets, continuing the endless cosmic cycle of birth and death. So, what's left behind after the supernova has faded? It all depends on the mass of the collapsed core. If the core is between 1.4 and about 3 times the mass of our Sun, it becomes a neutron star. This is an object so dense that a single teaspoon would weigh 1 billion tons. Imagine crushing a star bigger than our Sun into a ball the size of a city. That's a neutron star. These objects are the densest stable matter we know of. Their gravity is so intense that the surface is perfectly smooth. They often spin hundreds of times per second, beaming out radiation like cosmic lighthouses, which we observe as pulsars. The fastest known pulsar spins over 700 times a second, with its surface moving at nearly a quarter of the speed of light. But what if the core is even more massive? If it's more than about 3 times the mass of the Sun, then nothing, absolutely nothing in the known universe can stop the collapse. Gravity wins the final battle. The core continues to shrink, crushing itself past the neutron star stage, all the way down to an infinitely dense point called a singularity. In a fraction of a second, an event horizon forms around it, the point of no return. The core has become a stellar mass black hole. Gravity has literally punched a hole in the fabric of spacetime, creating a region from which nothing, not even light, can escape. But a supernova isn't the only way to make a black hole. Some truly enormous stars, more than 260 times the mass of our Sun, might skip the explosion altogether. Their cores collapse so violently that the entire star just vanishes. It collapses directly into a black hole in what's called a failed supernova. Astronomers have actually seen evidence of this, observing massive stars that seem to just disappear without a trace. In the early universe, the very first stars were even more massive, possibly hundreds of times the mass of our Sun. When they died, they may have collapsed directly into seed black holes, which then grew over billions of years by gobbling up gas and merging with other black holes to become the supermassive giants we see at the center of galaxies today. There's even a theory that dense clouds of primordial gas could have collapsed directly into a black hole without ever forming a star first. This could explain how some supermassive black holes got so huge so quickly in the early days of the cosmos. From the fiery death of a giant star to the quiet disappearance of a cosmic titan, the birth of a black hole is the ultimate triumph of gravity. Did you know that at the very heart of almost every large galaxy, including our own Milky Way, there's a monster lurking? I'm talking about supermassive black holes, cosmic behemoths containing the mass of millions or even billions of suns. These giants aren't just sitting there. They are the architects of the cosmos, shaping entire galaxies, dictating where and when stars are born, and creating the most energetic and awe-inspiring phenomena in the entire universe. Let's look at our own galactic backyard. Right at the center of the Milky Way, about 26,000 light-years away, sits Sagittarius A star, a supermassive black hole with the mass of 4 million suns. For decades, astronomers watched in fascination as stars danced around an invisible point, whipping around at incredible speeds. One of these stars, S2, completes its orbit every 16 years. At its closest point, it's moving at a blistering 2% of the speed of light. Tracking these stellar orbits gave us undeniable proof that a supermassive black hole anchors our galaxy. This incredible work was so groundbreaking that in 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for it. But how did these monsters get so big so fast? This is one of astronomy's greatest puzzles. We've seen evidence of them when the universe was less than 700 million years old, which is just a fraction of its current age. One idea, the light seed theory, suggests they started small, from the remnants of the very first generation of massive stars. But growing from 100 solar masses to billions would require them to eat non-stop for hundreds of millions of years. Another idea, the heavy seed theory, proposes they formed directly from the collapse of massive gas clouds, creating black holes of 100,000 solar masses almost instantly. The truth is, it was probably a mix of both, with different processes happening in different parts of the early universe. So, how does a supermassive black hole actually eat? They feed through something called an accretion disk. Imagine a swirling vortex of gas and dust spiraling inwards. As this material gets closer, friction causes it to heat up to millions of degrees, glowing brilliantly in X-rays and ultraviolet light. Believe it or not, a single feeding supermassive black hole can outshine its entire host galaxy, which contains hundreds of billions of stars. This process is incredibly efficient, converting about 10% of the mass that falls in directly into energy. That's far more efficient than the nuclear fusion that powers stars, making these black holes the most powerful engines in the universe. And it gets even more spectacular. Many of these feeding black holes don't just swallow matter, they also launch relativistic jets. These are powerful, narrow beams of plasma that shoot out into space at 99.9% of the speed of light, extending for millions of light years. The power these jets carry can sometimes exceed the brightness of the entire accretion disk. They are formed by magnetic fields twisted around the black hole, which extract its rotational energy. These jets play a crucial role in galaxy evolution by heating up the surrounding gas and preventing too many stars from forming. The galaxy M87 has a jet that extends over 5,000 light-years, with radio lobes that stretch 150,000 light-years across. That's bigger than our entire Milky Way galaxy. When a supermassive black hole is feeding voraciously, we call it a quasar. These are the most luminous, sustained objects in the cosmos. A single quasar can release 1,000 times more energy than an entire galaxy, all from a region smaller than our solar system. The brightest ones gobble up hundreds of solar masses every year. That's like eating one sun every few days. Quasars were much more common in the early universe when galaxies were constantly colliding, funneling huge amounts of gas to their centers. Today, most galaxies, including our own, host dormant, supermassive black holes that are barely feeding. On April 10, 2019, humanity saw the impossible. We saw the first ever picture of a black hole's event horizon. A global network of radio telescopes, called the Event Horizon Telescope, captured an image of the supermassive black hole at the center of the M87 galaxy, 55 million light-years away. The image showed a glowing orange ring surrounding a dark central shadow, just as Einstein's theories predicted. That bright ring is the light from the accretion disk, bent around the black hole by gravity. The shadow is the point of no return. This particular black hole has a mass of 6.5 billion suns, and its shadow is about 40 billion kilometers across. Then, in May 2022, we got another incredible picture, this time of Sagittarius A star, the black hole at the center of our own galaxy. Even though it's much closer, it was harder to photograph. At only 4 million solar masses, it's a lightweight compared to M87's giant, and its accretion disk changes in minutes, not days. Scientists had to develop new techniques, averaging thousands of images to get the final shot. The result was a spectacular confirmation that we live in a galaxy with a supermassive black hole at its core. Our entire solar system orbits this giant, taking 230 million years to complete one galactic lap at a speed of 230 kilometers per second. You might hear different names like Seyfert galaxies, quasars, and blazars. These all fall under the umbrella of active galactic nuclei, or AGN, which basically means a galaxy with a feeding supermassive black hole. The unified model suggests they are all the same thing, just viewed from different angles. If we see it from the side, it's a Seyfert galaxy. If we see it more face-on, it's a quasar. And if we're looking straight down the barrel of one of its jets, we see a blazar which has violently fluctuating brightness. The angle changes what we see, but the engine is always the same. What happens when galaxies collide? Their supermassive black holes eventually merge. Our Milky Way is currently on a collision course with the Andromeda galaxy, approaching at 110 kilometers per second. In about 5 billion years, they will crash. As their cores merge, Sagittarius A star and Andromeda's 100 million solar mass black hole will spiral towards each other for millions of years. Their final merger will create an incredible burst of gravitational waves, leaving behind a single, even more massive black hole of about 110 million solar masses in a new, larger galaxy. Today, most supermassive black holes are dormant, including our own Sagittarius A star. It's essentially starving, eating only about 1/1000th of an Earth's mass per year. But sometimes, it flares up when a comet or asteroid gets too close and is torn apart, briefly making it 10 to 100 times brighter. And every 10,000 years or so, an unlucky star wanders too close and gets shredded in what's called a tidal disruption event. This creates a brilliant flare that can last for months as the stellar material is consumed. It's amazing to think that these black holes, which make up only a tiny fraction of a galaxy's mass, about 0.1%, have such a profound impact. Through a process called AGN feedback, the jets and radiation from feeding black holes heat up the gas around them. This stops the gas from cooling down and forming new stars. This process explains why the most massive galaxies actually have fewer stars than we'd expect. In a way, these cosmic giants control the destiny of their entire galactic home. And the story is far from over. The James Webb Space Telescope is already revolutionizing our understanding of supermassive black holes. It's finding them in the earliest galaxies and helping us figure out how they formed in the first place. Every new observation uncovers new mysteries about these cosmic giants that have shaped the universe as we know it. The age of supermassive black hole discovery is really just beginning. Back in 1916, Albert Einstein came up with a wild idea. He predicted something called gravitational waves, actual ripples in the fabric of space-time, created when massive objects speed up. Think of it like dropping a bowling ball on a trampoline. These ripples, he said, would travel at the speed of light. But he also calculated they'd be unbelievably tiny, stretching space by less than the size of an atom's nucleus, even from the most violent explosions in the universe. Einstein himself was pretty skeptical we'd ever be able to find them. So what exactly are these gravitational waves? They're not like light or radio waves that travel through space. They are literally distortions of space itself. As a wave passes by, it stretches and squeezes everything in its path. Imagine a gravitational wave hitting you right now. You'd get a tiny bit taller and thinner, then shorter and wider over and over at the wave's frequency. Of course, the effect is so small you'd never feel it. Even waves from two black holes smashing into each other would only distort you by less than 1/10,000th, the width of a single proton. For decades, these waves were just a theory. But then, in 1974, two astronomers, Russell Hulse and Joseph Taylor, found something special: a binary pulsar. That's two super-dense neutron stars orbiting each other. They timed the orbits with incredible precision and discovered something amazing. The stars were slowly spiraling closer together. The orbit was shrinking by the exact amount Einstein's theory predicted if the system was losing energy by sending out gravitational waves. This was the first solid, though indirect, evidence that they were real, and it even won them the Nobel Prize in 1993. But to truly prove it, we needed to catch a wave in the act, and that's where LIGO comes in. The Laser Interferometer Gravitational Wave Observatory is an absolute marvel of engineering. It's made up of two identical detectors, one in Louisiana and one in Washington State. Each one is a giant L shape, with two vacuum tubes stretching out for 4 kilometers, or about 2.5 miles. Inside, a laser beam is split and sent down each arm, bouncing off mirrors at the ends. Normally, the light waves return and cancel each other out. But if a gravitational wave passes through, it stretches one arm while squeezing the other. This tiny change in distance knocks the light waves out of sync, creating a signal. The sensitivity is just mind-boggling. LIGO can spot changes in distance as small as 10 to the minus 19 meters. That's 1/10,000th the diameter of a proton. It's like measuring the distance to the nearest star over 4 light years away, with an accuracy smaller than the width of a human hair. Then came the moment that changed astronomy forever. September 14th, 2015, at just before 6 a.m. Eastern Time. A gravitational wave, created by two black holes colliding 1.3 billion light-years away, washed over the Earth. Both LIGO detectors, thousands of miles apart, picked up the exact same signal at the exact same time. It was a faint chirp that lasted less than 1/5 of a second, but it was unmistakable. The signal, S frequency and strength, increased exactly as predicted for two black holes spiraling into each other. Two black holes, one 36 times the mass of our Sun, and the other 29, danced their final dance, merged, and formed a new 62 solar mass black hole. The missing 3 solar masses weren't lost. They were converted directly into a blast of gravitational wave energy in a fraction of a second. The announcement in 2016 was one of the greatest scientific triumphs in history. So what does a black hole merger actually look like? It happens in 3 stages. First is the in-spiral. The 2 black holes orbit each other, getting closer and closer as they radiate away energy as gravitational waves. As they lose energy, they spin faster and their orbit tightens. In the final few seconds, when they're only a few hundred kilometers apart, they're whipping around each other hundreds of times per second. Then comes the merger itself, lasting just milliseconds. Their event horizons touch and combine into a single, violently distorted new black hole. In that instant, the power released in gravitational waves is greater than all the light from all the stars in the entire observable universe combined. Finally, there's the ringdowns. The misshapen new black hole wobbles and jiggles, like a struck bell, shedding the last of the waves until it settles into a stable, spinning black hole. But black holes aren't the only things that collide. On August 17, 2017, LIGO detected something new. Waves from 2 merging neutron stars. These are the ultra-dense cores left behind by dead stars, packing more mass than our Sun into a ball just 20 kilometers wide. And unlike silent black hole mergers, this collision lit up the sky. Seconds after the gravitational wave hit, space telescopes detected a burst of gamma rays. Within hours, telescopes all over the world spotted the source, a brilliant explosion called a kilonova, in a galaxy 130 million light-years away. The smash-up flung out super-dense neutron-rich material. This material rapidly created elements heavier than iron, including huge amounts of gold, platinum, and uranium. That one collision is thought to have created several Earths' worth of pure gold. These discoveries are also giving Einstein's theory of general relativity the ultimate stress test. Every signal we detect tests the theory in a new way, under the most extreme conditions imaginable. The gentle in-spiral tests one part of the equations, the violent merger tests another, and the final ring-down tests yet another. And every single time, Einstein's predictions have been proven correct with stunning precision. The neutron-star merger even proved that gravitational waves travel at exactly the speed of light, with an accuracy of 1 part in a quadrillion. This single measurement wiped out whole categories of alternative theories of gravity. A century later, Einstein's theory is still passing every test we can throw at it. With over 90 detections so far, we're learning some incredible new things. It turns out that stellar mass black holes are way more common and much more massive than we thought. Many are over 30 times the mass of our Sun, much bigger than any found in our own galaxy before. These cosmic collisions are happening all the time, thousands of them every single day across the universe. We've even found evidence for a whole new class of intermediate mass black holes, filling a long-standing gap in our knowledge. Each new chirp gives us a detailed cosmic police report, the masses, spins, and location of the objects involved, and another new test of fundamental physics. The neutron-star merger kicked off a brand new era of science, multi-messenger astronomy. This is where we combine gravitational wave signals with light, like gamma rays and visible light, to get a complete picture of an event. This one event alone gave us a new way to measure the expansion of the universe, helped us understand the exotic matter inside neutron stars, and confirmed where most of the universe's heavy elements come from. Scientists have published over 100 papers on just this one cosmic event, treating it like a Rosetta Stone for the cosmos. And this is just the beginning. The next generation of detectors will blow the doors wide open. In Europe, the planned Einstein telescope will have 10-kilometer arms built deep underground, making it 10 times more sensitive than LIGO. Here in the US, the Cosmic Explorer will have incredible 40-kilometer arms, and in the 2030s, we'll launch LISA, a space-based observatory with 3 spacecraft flying in formation, separated by 2.5 million kilometers. This will let us detect the slow, powerful waves from supermassive black holes merging at the centers of distant galaxies. The universe is literally ringing like a bell with the constant hum of gravitational waves. Black holes and neutron stars are merging thousands of times a day. Stars are exploding. Spinning neutron stars are sending out continuous waves. There's even a background hum left over from the Big Bang itself. As our detectors get better, we'll hear this cosmic symphony in more and more detail, finally witnessing the universe's most extreme events that have always been hidden from our view. Gravitational wave astronomy has given us a completely new sense to perceive the cosmos, totally different from looking at it with light. We can now detect things that are completely dark and invisible, like merging black holes, the chaos inside exploding stars, and maybe, just maybe, the very first echoes from the birth of the universe itself. Hawking radiation teaches us a profound lesson. Black holes, which seem eternal, are actually quantum objects that eventually evaporate. Classically, nothing can escape a black hole's event horizon, but quantum mechanics always finds a way. In the unimaginably distant future, black holes will be the last luminous objects in a cold, dying universe, before they too fade into nothingness. Back in 1935, Albert Einstein and physicist Nathan Rosen discovered something remarkable, hidden within the equations of relativity: wormholes. These are theoretical tunnels slicing through spacetime, connecting distant regions of the universe. These Einstein-Rosen bridges could link black holes, potentially allowing for travel across vast cosmic distances, or even more incredibly, through time itself. So what exactly is a wormhole? Think of it as a shortcut through space-time. It's like digging a tunnel through a mountain instead of climbing all the way over it. Imagine space-time as a huge sheet of paper. 2 points that are far apart on the surface could be brought close together by simply folding the paper and punching a hole through it. That's your wormhole. One end or mouth might be near Earth while the other is in a distant galaxy. Traveling through this wormhole could take just a few minutes instead of millions of years at the speed of light. Einstein's equations mathematically allow for these structures, but whether they actually exist in the physical universe is a completely different question. The original Einstein-Rosen bridge connects 2 black holes, but it comes with a fatal flaw. It pinches off faster than light can cross it. The wormhole's throat collapses before anything can get through, making it totally useless for travel. This structure is dynamic, collapsing almost immediately after it forms. Any particle or person trying to pass through would be crushed at the pinch-off point, where the throat contracts down to 0 size. Plus, this mathematical solution describes an eternal black hole, which probably doesn't exist in nature anyway, since real black holes form from collapsing stars. But what if a wormhole could stay open? Physicist Kip Thorne and his colleagues discovered that certain wormhole solutions could allow for two-way travel. These are called traversable wormholes. The catch: they require something called exotic matter with negative energy density to hold the throat open against the crushing force of gravity. Now, negative energy sounds like something straight out of science fiction, but quantum mechanics actually allows for it through phenomena like the Casimir effect. However, the amount of negative energy needed to stabilize a human-sized wormhole might be more than quantum mechanics permits. Even if it were possible, creating and maintaining such a structure would require technology far beyond anything we can even dream of. The Casimir effect is real-world proof that negative energy exists. If you place 2 uncharged metal plates just nanometers apart in a vacuum, they experience an attractive force. This happens because they exclude certain quantum wavelengths between them. The energy density between the plates becomes lower than the surrounding vacuum, and that's negative energy relative to empty space. Experiments have measured this effect with incredible precision. The problem is, the amount of negative energy you get from the Casimir effect is minuscule, nowhere near enough to hold open even a microscopic wormhole against collapse. Now, for the really wild part, traversable wormholes could potentially enable time travel. Imagine you have a wormhole with 2 mouths. You take one mouth on a journey at near light speed while the other stays put. Because of time dilation, the moving mouth ages slower. When you bring it back, the 2 mouths are now connected through the wormhole, but they exist at different points in time. You could step into one mouth in the year 2025 and walk out of the other in the year 2000. You've just traveled backward in time. But this opens a huge can of worms: causality paradoxes. Could you go back and prevent your own birth? This is the famous grandfather paradox. These paradoxes suggest that nature might have some rules in place to prohibit time travel. The great Stephen Hawking proposed what he called the chronology protection conjecture. Essentially, he believed the laws of physics conspire to prevent time travel in order to protect causality. As a wormhole gets closer to becoming a time machine, quantum effects might destabilize it catastrophically. Virtual particles could circulate through the wormhole infinitely, building up an infinite energy density that would instantly destroy it. Calculations suggest this quantum feedback loop would kick in just before the time machine could be activated. It seems nature has its own safeguards to protect its timeline. So, have we ever seen one? Despite decades of searching, astronomers have found zero evidence that wormholes exist naturally in the universe. None of our observations require a wormhole to explain them. Even the amazing gravitational wave detections from black hole mergers match predictions perfectly without any need for exotic wormhole signatures. While Einstein's equations allow for them mathematically, nature may simply not use these solutions. They could just be mathematical curiosities, possible on paper, but forbidden by deeper principles we haven't discovered yet. Of course, science fiction absolutely loves wormholes. You've got Stargate's intergalactic transit system, the gateway near Saturn in Interstellar, and Star Trek's Bajoran wormhole. These stories imagine perfectly stable, traversable wormholes that allow for instant travel across the galaxy. While incredibly entertaining, they tend to gloss over the enormous problems. Creating a wormhole would require manipulating spacetime on a scale far beyond any foreseeable technology. Stabilizing it would need vast quantities of negative energy that might violate the known limits of quantum physics. Even if we could build one, it would likely be one-way, unstable, or microscopic. Reality, it turns out, is far less accommodating than fiction. But what if wormholes are all around us, just too small to see? At the tiniest possible scale, the Planck scale, space-time might be a chaotic quantum foam, a seething sea of virtual particles and microscopic wormholes constantly popping in and out of existence. These quantum wormholes, far smaller than an atomic nucleus, could be fundamental features of space-time's very structure. Some physicists even speculate they could connect distant regions of space or even different universes. But before you get too excited, these would be completely useless for travel or communication. They're just fleeting quantum fluctuations, not stable tunnels. Some theories take this even further, suggesting that wormholes could connect our universe to baby universes, separate regions of space-time budding off from our own. During the cosmic inflation right after the Big Bang, quantum fluctuations might have created regions that inflated into their own independent universes, possibly connected to ours by wormholes. These baby universes would be causally disconnected from us, making the wormholes untraversable even in principle. They represent truly exotic possibilities where quantum mechanics, general relativity, and cosmology all intersect. So, could an advanced civilization ever build a wormhole? The challenges would be staggering. First, you'd have to create or find a wormhole, maybe by blowing up a piece of quantum foam or engineering space-time directly. Second, you'd need to stabilize it with that exotic matter. Third, you'd have to enlarge it to a usable size while keeping it stable. Fourth, you'd need to move the mouths to your desired locations. The energy requirements would dwarf anything humanity can produce. Even a Type 2 civilization capable of harnessing the power of an entire star might not have what it takes. For now, wormholes remain firmly in the realm of theoretical physics. They're permitted by the equations, but they've never been observed. They require exotic matter that might not exist in sufficient quantities, and they might be forbidden by the universe's own self-preservation rules. They tantalize us with the promise of interstellar shortcuts and time travel, but nature may have drawn a hard line between mathematical possibility and physical reality. For the foreseeable future, wormholes might just remain beautiful equations rather than traversable tunnels. Back in 1935, Albert Einstein and physicist Nathan Rosen were exploring the equations of relativity when they stumbled upon something extraordinary. Hidden in the math were theoretical tunnels through the fabric of space-time, connecting distant regions of the universe. These Einstein-Rosen bridges, or wormholes, could potentially link black holes, offering a tantalizing gateway across vast cosmic distances or maybe even through time itself. So, what exactly is a wormhole? Think of it as a cosmic shortcut. Imagine space-time is a giant sheet of paper. To get from one point to another, you'd usually travel across the surface. But what if you could fold the paper, bringing those 2 points close together, and then punch a hole straight through? That's a wormhole. One end, or mouth, could be here near Earth, while the other opens up in a distant galaxy. A journey that would take millions of years traveling at the speed of light could, in theory, take just a few minutes through the wormhole. Einstein's equations say these structures are mathematically possible, but whether they actually exist out there in the cosmos is a whole other question. The original Einstein-Rosen bridge design connects two black holes, but it has a fatal flaw. It pinches off faster than anything, even light can get through. The throat of the wormhole collapses almost instantly. So if you tried to travel through it, you'd be crushed at the center where the throat shrinks to zero size. This type of wormhole is also based on a concept called an eternal black hole, which probably doesn't exist in the real universe anyway, since actual black holes form from the collapse of massive stars. But don't lose hope just yet. Physicist Kip Thorne and his colleagues later figured out that some types of wormholes could actually allow two-way travel. The catch: to keep these traversable wormholes open and stop them from collapsing, you'd need something called exotic matter, stuff with negative energy density. Now, negative energy sounds like pure science fiction, but quantum mechanics actually allows for it in tiny amounts through phenomena like the Casimir effect. The problem is, the amount of negative energy needed to stabilize a wormhole big enough for a person to pass through might be physically impossible to gather. Even if it were possible, creating and controlling it would require technology far beyond anything we can currently imagine. Let's talk more about that negative energy. The Casimir effect is real-world proof that it exists. If you take two uncharged metal plates and place them incredibly close together in a vacuum, they will actually be pushed towards each other. This happens because the tiny space between the plates excludes certain quantum energy waves that exist everywhere else in the vacuum. This creates a region with lower energy density than the empty space around it, essentially negative energy. Experiments have measured this force precisely, but the amount of negative energy generated this way is minuscule, nowhere near enough to hold open even a microscopic wormhole. Now for the really wild part: time travel. A stable, traversable wormhole could theoretically become a time machine. Here's how. Imagine you have a wormhole with two mouths. You leave one mouth stationary, say near Earth, and you take the other one on a journey at near light speed. Thanks to time dilation, time will pass much slower for the moving mouth. When you bring it back, the two mouths, although connected, will exist at different points in time. You could step into one mouth in the year 2025 and emerge from the other in the year 2000. You've just traveled back in time. Of course, this opens up a huge can of worms, creating paradoxes. Could you go back and prevent your own birth? This is the famous grandfather paradox, and it suggests that nature might have some rules in place to prevent time travel. The great Stephen Hawking certainly thought so. He proposed the chronology protection conjecture, which basically says the laws of physics will conspire to prevent time travel and protect the timeline. How? As a wormhole gets closer to becoming a time machine, quantum effects might go haywire. Virtual particles which constantly pop in and out of existence could get caught in a feedback loop, circulating through the wormhole an infinite number of times. This would build up an infinite amount of energy, completely destroying the wormhole right before it could be used to violate causality. It seems the universe has its own built-in safety features to protect its own history. So, have we ever seen one? Despite decades of searching the skies, astronomers have found zero evidence that wormholes exist naturally. All of our observations, including the gravitational waves from merging black holes, perfectly match the predictions of relativity without needing any exotic structures like wormholes to explain them. While Einstein's math allows for them, it's possible nature just doesn't use that particular solution. They might be just a fascinating mathematical curiosity, possible on paper, but forbidden by some deeper physical principle we haven't discovered yet. Of course, science fiction absolutely loves wormholes. You've got the Stargate network, the gateway near Saturn in Interstellar, and the Bajoran wormhole in Star Trek. These stories imagine stable, reliable wormholes that make galactic travel as easy as catching a train. While it's incredibly fun to imagine, they conveniently ignore the colossal problems. Creating a wormhole would mean manipulating space-time on a scale we can't even comprehend. Stabilizing it requires massive quantities of negative energy that might be impossible to create. And even if we could build one, it would likely be unstable, one-way, or microscopically small. Reality, as usual, is a lot trickier than fiction. But what if wormholes are all around us, just too small to see? At the tiniest possible scale, the Planck scale, some physicists believe space-time isn't smooth, but is actually a chaotic quantum foam. This subatomic realm might be teeming with microscopic wormholes, constantly winking in and out of existence. These quantum wormholes could be a fundamental part of space-time's structure, maybe even connecting different universes. However, they're just fleeting quantum fluctuations, not stable tunnels, so they'd be completely useless for travel or communication. Some theories take this even further, suggesting that wormholes could connect our universe to baby universes, separate bubbles of space-time that budded off from our own, perhaps during the Big Bang. These other universes would be completely disconnected from ours, making the wormholes between them untraversable. It's an exotic idea sitting at the crossroads of quantum mechanics, relativity, and cosmology, pushing the very limits of our understanding. Let's imagine for a moment an incredibly advanced civilization trying to build one. The challenges would be staggering. First, they'd have to create a wormhole, maybe by tearing the fabric of space-time or amplifying one from the quantum foam. Then, they'd have to gather enough exotic matter to stabilize it and inflate it to a usable size. Finally, they'd have to move the mouths to their desired locations. The energy required would be astronomical, likely beyond even a civilization capable of harnessing the entire power of its star. So will wormholes forever remain a dream? For now, they are firmly in the realm of theoretical physics. They are permitted by the equations, but we've never seen one. They require exotic matter that we don't know how to create in large amounts, and they might even be forbidden by nature's own laws to protect causality. They continue to tantalize us with the promise of cosmic shortcuts and journeys through time, but nature may have drawn a firm line between what's mathematically possible and what's physically real. Wormholes might just be beautiful equations, destined to remain on paper rather than becoming tunnels through the stars. Our universe kicked off 13.8 billion years ago in the Big Bang, a colossal explosion expanding from an unbelievably hot and dense point. But what was there before the beginning? What exists beyond the edge of our observable universe? And what if, just what if, black holes are the secret doorways to other universes? These aren't just late-night thoughts. They are questions that push the very fabric of physics to its absolute breaking point. The multiverse is an idea that sounds straight out of a comic book, but it's a serious hypothesis. Imagine our universe is just one bubble in a vast cosmic ocean with countless other bubble universes floating alongside it. These parallel worlds might have entirely different laws of physics, different constants, maybe even a different number of dimensions. Some could be eerily similar to ours, while others would be utterly alien beyond our wildest imagination. This concept isn't just a fantasy. It emerges naturally from some of our most promising theories, like eternal inflation, string theory, and quantum mechanics. The catch? These other universes might be forever beyond our reach, making the whole idea incredibly difficult, if not impossible, to prove. Now let's get even wilder. Some physicists propose a mind-bending idea. Every black hole is a cosmic parent, giving birth to a brand new universe. When a star collapses under its own gravity, instead of being crushed into an infinitely dense point, a singularity, it might bounce. This black hole Big Bang could inflate a whole new region of spacetime, creating a baby universe hidden from our view. From our perspective, it's just a black hole, but inside, beyond the event horizon, a new cosmos is born, with its own space and its own time. This paints a picture of a grand cosmic family tree, where universes create black holes, which in turn create more universes in an endless cycle of cosmic reproduction. Physicist Lee Smolin took this idea a step further with his theory of cosmological natural selection. Think of it like cosmic Darwinism. Universes that are good at making black holes essentially have more offspring. They pass down their fundamental physical laws to these baby universes, but with slight, random variations. Over countless cosmic generations, this process would favor universes like ours that are exceptionally good at producing black holes. It's a fascinating thought. Our universe might be the product of eons of cosmic evolution, fine-tuned for black hole creation. This theory even makes predictions we could one day test, although our current technology isn't quite there yet. Einstein's equations of general relativity have a strange twin to black holes, white holes. They're the exact time-reversed version. Black holes are the ultimate cosmic traps. Matter falls in, but nothing gets out. White holes would be the ultimate cosmic fountains, spewing matter and energy out, while letting nothing in. Theoretically, you could connect a black hole to a white hole with a wormhole, creating a tunnel through spacetime. Matter falls into the black hole and shoots out of the white hole somewhere else, or maybe even sometime else. The problem is, white holes are thought to be incredibly unstable. They'd likely collapse or disappear in an instant. So far, astronomers haven't found a single shred of evidence that they actually exist. Ready for a real head-scratcher? What if our entire universe is inside a black hole that exists in some larger, higher dimensional space? It sounds bizarre, but the math behind an expanding universe and the math describing the interior of a black hole are surprisingly similar. From the outside, our universe would just look like a regular black hole. But for us on the inside, we experience it as the expansion of space itself. This idea could even solve some cosmic puzzles, like why the universe looks so uniform in every direction. It would all be part of one single connected region. This is highly speculative, of course, more of a mathematical curiosity than a proven theory, but it's a tantalizing possibility. One of the most profound ideas to come from black hole physics is the holographic principle. It suggests that all the information contained in a 3D volume of space, like our universe, can be described by a theory living on its 2D boundary. Think of a hologram on your credit card. It's a 2D surface that contains all the information to project a 3D image. The first clue came from black holes. Their information content, or entropy, is proportional to the surface area of their event horizon, not their volume. This radical idea suggests our 3D reality might be a holographic projection from information encoded on a distant 2D surface, fundamentally changing our understanding of space, time, and gravity. String theory, our leading candidate for a theory of everything, proposes that the fundamental constituents of reality aren't particles but tiny vibrating strings of energy. To make the math work, this theory requires more than our familiar 4 dimensions of space and time. It needs 10 or 11 dimensions. The extra dimensions are thought to be curled up into incredibly tiny, complex shapes. In this framework, black holes are intricate objects with structures extending into these hidden dimensions. The theory also predicts that if we could smash particles together with enough energy, we might create microscopic black holes that would evaporate almost instantly, providing the first concrete evidence for both extra dimensions and quantum gravity. Let's go back to the beginning. Eternal inflation theory suggests that the rapid expansion of the early universe, known as cosmic inflation, never truly stopped everywhere. Instead, it's like a pot of boiling water, constantly bubbling. Different regions of space stop inflating at different times, forming self-contained bubble universes. Each bubble is a unique cosmos, with its own set of physical laws determined by how inflation ended there. Our universe is just one of these bubbles in an eternally inflating, ever-growing multiverse. Within this grand cosmic foam, black holes could be the gateways connecting our bubble to others, or even the seeds that create new bubble universes from scratch. Recently, physicists have uncovered a shocking connection between 2 seemingly unrelated concepts, wormholes and quantum entanglement. This is known as the ER equals EPR conjecture. ER stands for Einstein-Rosen bridges, which are wormholes, and EPR refers to the spooky action at a distance of entangled particles. The conjecture proposes that any 2 entangled particles are secretly connected by a microscopic wormhole. This mind-blowing idea suggests that space-time geometry and quantum mechanics are two sides of the same coin, the same fundamental reality described in different languages. Black holes, being masters of both gravity and quantum mechanics, are the perfect cosmic laboratories for testing this incredible link. Let's journey to the very end of time. In the distant, distant future, long after the last star has burned out and galaxies have drifted apart, black holes will be the last major objects left in the cosmos. But even they are not eternal. They will slowly, painstakingly evaporate through Hawking radiation. For the largest supermassive black holes, this process will take an unimaginable amount of time, a 1 followed by 100 zeros, years. When the very last black hole finally radiates away into a puff of light and particles, it will mark the true end of all structure in the universe, leaving behind nothing but a cold, empty, and eternally expanding void. For all its fascinating possibilities, the multiverse faces one giant hurdle. How can we test it? By their very nature, other universes might be forever beyond our observation. This leads some physicists to argue that multiverse theories aren't really science at all, but more like philosophy, since they can't be falsified. Others push back, arguing that since these ideas emerge from our best-tested theories, like inflation and string theory, they have scientific merit, even if direct proof is out of reach. It's a fiery debate at the frontiers of physics about what science is and where its limits lie when we explore the unobservable. Black holes are more than just cosmic vacuum cleaners. They are gateways to the deepest questions of existence. What is space-time made of? How do gravity and quantum mechanics finally unite? Is our universe a one-off creation, or just one among an infinite number of others? Do black holes hold the secrets to our origin and the key to creating new realities? These questions stretch our imagination to its limits and remind us, with a sense of profound wonder, just how much we have yet to learn about the incredible cosmos we call home. Ever looked up at the night sky and wondered what's hiding in the darkness? Some of the universe's biggest secrets are completely invisible. I'm talking about black holes. They don't emit any light, so you can't just point a telescope and see one. They're nature's perfect voids. So how do we study something we literally can't see? Well, it turns out you don't look for the black hole itself, you look for the chaos it creates all around it. One of the first clues came from X-rays. Imagine a black hole in a cosmic dance with a regular star. The black hole's immense gravity starts stealing gas from its partner. This stolen gas doesn't just fall in, it spirals down into what's called an accretion disk, kind of like water swirling down a drain. As the gas gets closer, friction and gravity heat it up to millions of degrees, making it glow incredibly brightly, not in visible light, but in X-rays. Telescopes in space can pick up these X-ray signals. That's exactly how we found Cygnus X1 back in the 60s, the first real candidate for a stellar mass black hole. The flickering of these X-rays, as clumps of hot gas plunge into the abyss, is a dead giveaway. So we can detect them, but how do we weigh something invisible? It's all about gravity and motion. In those binary systems, we can watch the visible star. As it orbits its unseen partner, it wobbles. By measuring the speed of that wobble using something called the Doppler effect, how its light shifts to blue as it moves towards us and red as it moves away, we can calculate the mass of the object it's orbiting. If that invisible object is more than 3 times the mass of our sun, it's too heavy to be anything else. It has to be a black hole. For the supermassive giants at the center of galaxies, we do the same thing, but with stars orbiting the galactic core. The faster those stars are whipping around, the more massive the black hole must be. The accretion disks themselves have some mind-bending tells. As we look at the light coming from them, specifically from elements like iron, we see something strange. The light is smeared out and distorted. This is because one side of the disk is spinning towards us at nearly the speed of light, while the other side is spinning away. This extreme speed, combined with the black hole's intense gravity, stretches and squashes the light waves. By studying these distorted signals, we can even figure out how fast the black hole is spinning. It's like a cosmic fingerprint that screams, "Black hole here." Einstein himself gave us another way to find them. He predicted that massive objects can bend the fabric of space-time, and that includes bending light. This is called gravitational lensing. When a black hole drifts in front of a distant star, its gravity acts like a lens, focusing the starlight and making it appear to brighten temporarily in a very specific way. This micro-lensing lets us spot lone, wandering black holes that aren't actively feeding on anything. For the supermassive black holes, the effect is even more dramatic. They can warp the light from an entire galaxy behind them into stunning arcs, or even a complete circle called an Einstein ring. The amount of distortion tells us the mass of the black hole doing the lensing. Radio telescopes have been a game changer. Many supermassive black holes don't just swallow matter, they launch colossal jets of particles at nearly the speed of light. These jets are incredibly bright at radio wavelengths, and we can trace them for millions of light years across space. To get a closer look, astronomers link radio telescopes across the globe in a technique called Very Long Baseline Interferometry. By combining their power, they create a virtual telescope the size of Earth, giving us the razor-sharp resolution needed to see the area right around the event horizon. This is the very technique that finally allowed us to take a picture of a black hole. And that brings us to the Event Horizon Telescope, or EHT. It's not one telescope, but a worldwide network of them, all working together. In April 2017, they all pointed at the supermassive black hole in the M87 galaxy. They recorded so much data, about 350 terabytes every single day, that it had to be physically flown on hard drives to processing centers. Using atomic clocks for perfect synchronization and some incredibly clever algorithms, scientists pieced together the signals to reconstruct an image. The result was that iconic, world-famous picture of a glowing ring of light surrounding a dark shadow. The first ever direct image of a black hole, S event horizon, 55 million light-years away. Next, the EHT team turned their sights on the black hole at the center of our own Milky Way, Sagittarius A star. This was actually a harder target. Even though it's much closer, it's also much smaller, and its surroundings change incredibly fast. In a matter of minutes, not days like M87. It was like trying to take a clear picture of a spinning top. The team had to invent new methods, taking thousands of images and averaging them out to reveal the stable, underlying structure. The image they released in May 2022 was another triumph, perfectly matching predictions and looking just like M87's black hole, just scaled down. While black holes are dark, their neighborhoods can be bright in other ways. Our galactic center is shrouded in dust, but infrared telescopes can peer right through it. Using amazing technology called adaptive optics, which corrects for the blurring of our atmosphere, ground-based telescopes can get images as sharp as those from space. For decades, astronomers have used this to track individual stars as they orbit Sagittarius A star. Watching stars like S2 complete their full 16-year orbits allowed us to map the black hole S gravity with incredible precision and confirm Einstein S theories in the most extreme environment imaginable. Then came a totally new sense: gravitational waves. When massive objects like black holes collide and merge, they send ripples through the fabric of space-time itself. Detectors like LIGO can hear these waves. The signal, a characteristic chirp that gets higher in pitch and louder, tells us everything about the merging black holes, their masses, their spins, and how far away they are. Unlike light, these waves travel through the universe completely unobstructed, giving us a direct line to the most violent events in the cosmos and revealing a population of black holes we never knew existed. And the future looks even brighter, or should I say, clearer. The next generation Event Horizon Telescope will have more telescopes observing at higher frequencies, aiming to create actual movies of matter swirling into a black hole. Space-based gravitational wave detectors, like LISA, will be able to detect the mergers of supermassive black holes across the universe. New ground-based giants like the Extremely Large Telescope will track stars even closer to our galaxy Oumuamua central black hole. Each new tool will peel back another layer of mystery. This all leads to the era of multi-messenger astronomy. Imagine combining all these tools, seeing the gravitational waves from a black hole merger, and at the same time seeing the event in X-rays, radio waves, and visible light. Each messenger tells a different part of the story. The gravitational waves reveal the raw dynamics of the merger, while light from across the spectrum tells us about the environment and the aftermath. This combined view gives us a complete picture that was unimaginable just a few years ago. From those first faint X-ray whispers in the 1960s to direct images and the sound of space-time ringing, our ability to perceive the unseeable has grown exponentially. Black holes have transformed from a mathematical curiosity into a fundamental part of observational astronomy. And with every new discovery, we find they are more common, more complex, and more important to the life of the universe than we ever dreamed. The adventure of exploring these cosmic monsters has only just begun. You might think of black holes as just destructive monsters, but the truth is far more complex. They aren't just passengers in galaxies. They're the architects of galactic evolution. Despite containing only a tiny fraction of their galaxy's mass, these cosmic giants regulate star formation, control gas flows, and ultimately determine their host galaxy's fate. Galaxies and their central black holes grow together in an intricate cosmic dance, shaping the universe as we know it. So, how do we know this? Astronomers discovered a remarkable clue called the M-sigma relation. It shows that a galaxy's central black hole mass is tightly linked to how fast stars are moving in the galaxy's central bulge. More massive black holes live in galaxies with faster moving stars. This connection is incredibly precise, suggesting that black holes and galaxies are constantly influencing each other's growth. It's like the black hole somehow knows what's happening to stars thousands of light years away. This points to some fundamental feedback mechanism linking the very smallest and largest scales in a galaxy. This mechanism is called active galactic nucleus feedback, or AGN feedback. It's how supermassive black holes control their galaxies. When a black hole actively feeds on surrounding gas and dust, the process releases immense energy. This radiation and powerful jets heat the surrounding gas to millions of degrees, which stops it from cooling down and collapsing to form new stars. This process regulates star formation, and it tests the reason why the most massive galaxies actually produce fewer stars than you'd expect. Without this AGN feedback, giant galaxies would be crammed with way more stars than we observe. Black holes are basically cosmic thermostats, keeping their galaxies in a perfect equilibrium. Sometimes this feedback gets turned up to 11. This is called quasar mode feedback, and it happens during periods of intense black hole growth. The brilliant light from a feeding supermassive black hole, a quasar, drives powerful winds that blast through the galaxy at thousands of kilometers per second. These winds can expel enormous amounts of gas, effectively shutting down star formation for good. They can carry away so much gas that the galaxy is permanently changed. Quasar mode feedback is why we see massive elliptical galaxies that are red and dead. They blew out their gas supply billions of years ago because of these black hole-driven winds and haven't formed new stars since. But feedback isn't always so dramatic. There's also a gentler process called radio mode feedback. This operates in galaxies where the central black hole is either dormant or just snacking lightly. Relativistic jets, visible in radio wavelengths, shoot out from the black hole and inflate enormous bubbles in the surrounding hot gas. We can see these cavities clearly with X-ray telescopes. As these bubbles rise, they stir the gas and deposit energy, preventing it from cooling and falling back onto the black hole in a runaway process. It's a self-regulating cycle. If gas starts to cool and accrete, the black hole switches on, heats it up again, and the process repeats. This can keep a galaxy stable for billions of years. Things get really exciting when galaxies collide. These mergers dramatically affect both the galaxies and their central black holes. As galaxies crash together, gravitational forces funnel gas toward the galactic centers. This triggers a massive burst of star formation, and at the same time, feeds both supermassive black holes, causing them to light up as dual quasars blazing near each other. Over millions of years, the two black holes spiral closer and closer, until they merge in a cataclysmic event that sends gravitational waves rippling across the universe. Our own Milky Way is on a collision course with the Andromeda Galaxy, and this is the exact scenario that will play out in our distant future. This feedback process also explains a pattern called cosmic downsizing. It is the observation that the most massive galaxies formed their stars early in the universe and then stopped, while smaller galaxies are still creating stars today. It all comes back to AGN feedback. In the early universe, massive galaxies hosted massive black holes that grew rapidly. Once they became big enough, their feedback was powerful enough to expel all the gas, quenching star formation forever. Meanwhile, smaller galaxies with smaller black holes just couldn't generate that much power, so their star formation continues. When you look at galaxies, they generally fall into two main groups: a blue cloud of star-forming galaxies and a red sequence of old dormant ones. In between them is a sparsely populated area called the Green Valley. This is a transition zone where galaxies are rapidly shutting down star formation. AGN feedback is the driver. When a galaxy's black hole activates, it expels the gas in about 100 million years, a blink of an eye in cosmic terms. The galaxy quickly turns red as its last generation of blue stars dies out. The fact that the Green Valley is so empty proves this transition happens incredibly fast, just as our models of AGN feedback predict. Now let's bring in another invisible giant: dark matter. Supermassive black holes and dark matter halos actually grow together. Galaxies form inside these immense invisible halos of dark matter. And it turns out, the more massive the dark matter halo, the more massive the galaxy and its central black hole. That M-sigma relation we talked about earlier probably comes from this, because the speed of the stars is a good indicator of the gravitational pull of the dark matter halo. It's a beautiful connection between dark matter, visible matter, and black holes, revealing the hierarchical way the universe is built. Black holes even helped make the universe transparent. In the first billion years after the Big Bang, space was filled with a fog of neutral hydrogen. An event called cosmic reionization cleared this fog, when ultraviolet radiation from the first stars and quasars ionized the hydrogen. While stars did most of the work, those early, brilliant quasars, powered by supermassive black holes, were significant contributors. By studying the light from the most distant quasars, we can see how this fog cleared over time. In a way, black holes helped light up the universe. So how do we piece all of this together? We use powerful telescopes to look back in time. Deep space surveys like the Hubble Ultra Deep Field show us galaxies at different stages of their lives. Astronomers can measure star formation rates, black hole masses, and AGN activity across different cosmic epochs. The data confirms it. Black holes and galaxies grow in lockstep. They both hit their peak activity when the universe was just 2 to 3 billion years old, and have been quieting down together ever since. To test these ideas, we use supercomputer simulations to build virtual universes. Early simulations that didn't include black hole feedback failed completely. They created massive galaxies with far too many stars. But once physicists added AGN feedback into the models, everything clicked. Modern simulations that include black hole physics and dark matter produce virtual galaxies that look almost identical to real ones. This is powerful confirmation that supermassive black holes are absolutely essential to understanding how galaxies form and evolve. So in the end, galaxies and their supermassive black holes are cosmic partners, their fates intertwined across billions of years. The black hole regulates its galaxy, and the galaxy feeds its black hole. First up, meet the cosmic runaways, hypervelocity stars. Imagine a star moving so fast it's literally escaping our Milky Way galaxy, shot out like a cosmic cannonball. We're talking thousands of kilometers per second. How does this happen? Our own galaxy's supermassive black hole, Sagittarius A/C, acts like a giant gravitational slingshot. When a pair of stars gets too close, one is captured by the black hole's immense gravity, while its partner is violently ejected, flung into the lonely void of intergalactic space. But getting flung out of the galaxy might be getting off easy. If a star wanders just a little too close to a supermassive black hole, it faces a far grislier fate, a tidal disruption event, or TDE. The black hole's tidal forces, the same kind of force that causes tides on Earth but millions of times stronger, stretch the star like spaghetti. It's ripped apart into a long stream of stellar guts. About half of this material gets devoured by the black hole, while the other half is blasted away at incredible speeds. As the debris spirals inward, it heats up to millions of degrees, creating a flare so brilliant it can outshine the entire core of its galaxy for months or even years. Astronomers spot dozens of these stellar death cries every year, and each one gives us a unique window into the black hole's mass, its spin, and the chaotic physics of how they feed. Some are even periodic, with a star on a risky elliptical orbit getting partially shredded with every close pass. And the chaos doesn't stop there. Supermassive black holes don't just eat, they also spit. They launch relativistic jets, the most powerful particle accelerators in the universe. These are colossal beams of plasma, accelerated to 99.9% of the speed of light. Forget exploding stars. A single jet can carry more energy and stretch for millions of light years, far beyond the confines of its own galaxy. The engine behind this is mind-bending. Twisted magnetic fields tap directly into the black hole is rotational energy, pulling particles from the very edge of spacetime and launching them outwards. As these particles spiral along the magnetic field lines, they release a torrent of radiation, from radio waves all the way up to gamma rays. These jets can persist for millions of years, continuously pumping unbelievable amounts of energy into the cosmos, creating vast radio lobes that dwarf entire galaxies. Now, what happens if we're staring right down the barrel of one of these cosmic fire hoses? We see a blazer. Blazars are simply active galactic nuclei where we have a direct line of sight down the jet. This special orientation has a dramatic effect called relativistic beaming. Think of it like a cosmic lighthouse. The radiation from the plasma moving towards us at nearly the speed of light is incredibly amplified, making the blazer appear fantastically bright. They are violently variable, capable of changing their brightness by a factor of 10 or more in just a few hours. This happens as superfast clumps of plasma roar past our line of sight. They light up the entire electromagnetic spectrum, from radio waves to the highest energy gamma rays, accelerating particles to energies that make our largest human-made accelerators, like the Large Hadron Collider, look like toys. But not all extreme X-ray sources are supermassive. Meet ultraluminous X-ray sources, or ULXs. These are cosmic enigmas, shining with an X-ray brightness that seems to defy the laws of physics. They blast out more radiation than should be possible for an object of their mass, a rule known as the Eddington limit. So what are they? Some might be the long-sought intermediate mass black holes, weighing in at hundreds or thousands of times the mass of our Sun. Others could be regular stellar mass black holes, or even neutron stars that are binge-eating at super Eddington rates. They're so bloated with infalling material that the radiation is forced out through narrow funnels or jets, allowing them to shine brighter than they should. ULXs are pushing the boundaries of what we thought we knew about how black holes feed. Black holes don't just destroy things, they can also get kicked out of their own homes. When two black holes spiral together and merge, the process can release a powerful blast of gravitational waves. If these waves are emitted unevenly, they create a gravitational kick, launching the newly merged, larger black hole at incredible speeds, up to 5,000 kilometers per second. That's fast enough to escape even the most massive galaxies. Imagine a galaxy suddenly losing its central anchor. Astronomers are actively searching for these recoiling black holes, looking for active galactic nuclei that are oddly offset from the center of their host galaxies. If this is a common occurrence, it could completely change our models of how galaxies evolve over cosmic time. Downsizing from galactic centers, let's look at X-ray binaries. These are stellar mass black holes locked in a dramatic dance with a companion star. They're essentially miniature quasars, sometimes called microquasars. The most famous one, Cygnus X1, was actually the very first object confirmed to be a black hole. In these systems, the black hole's powerful gravity strips gas from its companion. This gas forms a superheated accretion disk that spirals around the black hole, reaching millions of degrees and blasting out intense X-rays. Just like their supermassive cousins, some of these microquasars launch powerful jets of their own, creating glowing radio lobes that flicker in and out of existence. They are fantastic laboratories for studying the physics of accretion, showing wild variability on timescales from milliseconds to years. And just when we think we've seen it all, the universe throws us another curveball: quasi-periodic eruptions, or QPEs. This is a brand new discovery. Certain galaxies have been observed to have these incredibly regular spikes in their X-ray brightness, flashing with clockwork precision every few hours. What could cause such a rhythm? The leading theory is a cosmic dance of extreme gravity. It suggests a smaller object, maybe a white dwarf or another small black hole, is orbiting a central supermassive black hole on a very eccentric egg-shaped path. Each time it makes a close pass, it triggers an instability in the accretion disk, producing a predictable flare of X-rays. QPEs are giving us an unprecedented way to probe the warped spacetime right near a black hole's event horizon. Black holes are also masters of disguise. Take the changing look quasars. For years we thought the difference between types of quasars was just a matter of our viewing angle, but some of them are changing their appearance right before our eyes over just a few years. A cosmic blink. A bright quasar can suddenly dim and transform its entire spectrum, or vice versa. Our viewing angle can't change that fast. Instead, it seems the black hole's feeding rate itself is changing dramatically. This could be caused by the sudden snack of a tidally disrupted star, or some major instability in the accretion disk. These chameleons prove that a black hole's diet is far more frantic and variable than we ever imagined. We've learned to see the universe's most violent events through gravitational waves, but what about the ones we miss? When a black hole merges with a neutron star, it should produce a gamma-ray burst, the most powerful explosion in the universe. The catch? These bursts are shot out in narrow beams. If Earth isn't directly in the path of that beam, we see nothing. So for every gamma-ray burst we detect, there could be hundreds of orphan events. We detect the gravitational waves from the collision, but the flash of light is pointed somewhere else. As our gravitational wave detectors get more sensitive, we'll start to find these orphans, giving us a true census of just how often these cataclysmic mergers happen. So, how big can a black hole get? The answer is terrifyingly big. The champions are the ultra-massive black holes. The quasar TON 618, for example, hosts a black hole that weighs 66 billion times the mass of our Sun. Its event horizon is so vast, our entire solar system would fit comfortably inside. And it might not even be the biggest. The black hole at the center of the Phoenix cluster could be over 100 billion solar masses. How do they get so monstrously large? It's a huge mystery. They would have had to feed constantly at their maximum possible rate for billions of years. These giants are pushing our theories of black hole growth to their absolute limits. Finally, not all black holes stay put. Many are wanderers drifting through the star fields of galaxies. These could be intermediate mass black holes from dwarf galaxies that were swallowed up by a larger one, or even supermassive black holes kicked out of their own galactic centers. Many would be completely invisible, their presence only given away by the gravitational tug they exert on passing stars. Others might occasionally snag some interstellar gas, briefly flaring up in X-rays or visible light before fading back into obscurity. Astronomers estimate that hundreds, maybe even thousands of these wandering black holes could be silently roaming our own Milky Way right now. From stars torn to shreds and jets that span galaxies, to wandering monsters and cosmic lighthouses, black holes are the engines of the universe's most extreme phenomena. Each new observation is a peek into a cosmic laboratory where matter, energy, and space-time itself are pushed to their breaking point. They constantly remind us that the universe is far more strange, violent, and wonderful than we can possibly. Black holes have captured the human imagination like few other scientific concepts. From theoretical curiosities to cultural icons, they've become synonymous with mystery, danger, and the unknown. But how did simple mathematical solutions to Einstein's equations become staples of science fiction and our collective consciousness? Science fiction writers embraced black holes long before astronomers even confirmed their existence. The 1979 Disney film, The Black Hole, famously depicted them as cosmic whirlpools leading to heaven and hell. In the world of Star Trek, black holes were clever plot devices for time travel and jumping to parallel universes. While these early depictions weren't exactly scientifically accurate, they absolutely captured the public's imagination and sparked a massive interest in extreme physics. They portrayed black holes as cosmic mysteries just waiting to be explored, firmly establishing them as symbols of the final frontier. Then, the 2014 film Interstellar came along and completely revolutionized how we see black holes. The filmmakers consulted with physicist Kip Thorne to ensure scientific accuracy. The result was the black hole Gargantua, rendered using actual general relativity equations. It showed the public what a black hole might truly look like: a glowing accretion disk with its light gravitationally lensed into a mind-bending pattern around a dark shadow. The film also accurately depicted time dilation, where 1 hour on Miller's planet equaled 7 years elsewhere. Interstellar proved that scientifically accurate black holes are far more visually spectacular than anything artists could simply invent. And then in April 2019, science fiction became science fact. The Event Horizon Telescope released the first ever direct photograph of a black hole, and it became a global sensation. The image was on every news site, it trended across all social media, and it even became a meme. That glowing orange ring looked remarkably similar to Interstellar's Gargantua, which was an incredible vindication for both Einstein's century-old theory and modern computational models. This single image transformed black holes from an abstract concept into a photographed reality, cementing their place in our minds as real cosmic objects, not just theoretical ideas. Of course, popular culture has also promoted a few common misconceptions. For one, black holes are not cosmic vacuum cleaners, indiscriminately sucking up everything nearby. If you replaced our sun with a black hole of the exact same mass, the planets would just continue to orbit it normally. You'd have to get incredibly close within a few Schwarzschild radii for its tidal forces to become dangerous. Also, black holes don't just roam around space devouring stars. Most are stationary at the centers of galaxies or are in binary systems with another star. They're only a danger to objects that venture extremely close, not the omnivorous predators they're often made out to be. Science fiction also loves using black holes for time travel, falling through one to reach the past or a parallel universe. While a black hole's extreme time dilation does make forward time travel possible, traveling backward remains firmly in the realm of fiction as far as we know. And the idea of a wormhole through a black hole, if one could even exist, it would likely be a one-way, instantly fatal trip. No information can survive crossing the event horizon in a way we could retrieve it. Real black holes are dead ends, not passages to somewhere else. Video games have taken our fascination to a new level by allowing us to experience black holes interactively. The game Outer Wilds features a stunning, scientifically inspired black hole at the universe's end. Elite Dangerous includes realistic black holes and neutron stars that actually affect gameplay. And the Universe Simulator Space Engine renders black holes using relativistic equations. These games educate while they entertain, teaching players about things like gravitational lensing and time dilation through gameplay, making these complex concepts accessible to everyone. Black holes also inspire artists across all mediums. Musicians reference them metaphorically. The band Muse even titled an album with themes of entropy and black holes. Visual artists create incredible interpretations, from abstract representations to detailed scientific visualizations. Black holes have come to symbolize mystery, endings, transformative forces, and the sublime power of nature. They've become cultural shorthand for concepts that transcend their literal meaning, like a point of no return or an inescapable attraction. And that's because black holes function as powerful metaphors in our everyday language. We talk about emotional black holes, like grief or depression that seems to pull everything into darkness. There are financial black holes that devour resources without end. We even describe bureaucracies where messages just seem to vanish as information black holes. These metaphors work so well because black holes embody universal concepts: inescapable forces, irretrievable loss, and mysterious depths. Ultimately, black holes are like gateway drugs to science. Their inherent drama makes them perfect educational tools. Planetarium shows on black holes attract huge audiences. YouTube videos explaining them get millions of views. Books like Stephen Hawking's A Brief History of Time became bestsellers partly due to our fascination with them. They show that cutting-edge physics can be exciting and accessible, inspiring new generations of scientists and keeping the public interested in fundamental research. Of course, this power can also generate fear. When CERN's Large Hadron Collider first started up, some people feared it would create black holes that would destroy Earth. This was scientifically baseless, but it shows how black holes can evoke primal fears of the unknown and inescapable doom. Tabloids also love to sensationalize stories about nearby black holes threatening our planet. As our observations improve and theories develop, our cultural depictions of black holes will continue to evolve. Future films and games will surely incorporate new discoveries. Maybe virtual reality will let us experience falling into a black hole with unprecedented realism. Each scientific advance enriches our cultural representations, creating a feedback loop where science informs culture and culture inspires scientific interest. Black holes have truly transcended their scientific origins to become cultural icons. They represent humanity's quest to understand the cosmos, symbolizing both what we know and what remains a mystery. From equations on a page to stunning imagery to powerful metaphors, black holes demonstrate the power of science to reshape not just our knowledge, but our culture itself. Even after all we've learned, black holes are still wrapped in cosmic mystery. What really happens inside a singularity? Is information that falls in lost forever? How did supermassive black holes get so huge, so fast, in the early universe? Are there millions of medium-sized black holes hiding out there? And can we ever directly see the faint whisper of Hawking radiation? These are the giant questions that are pushing the next wave of black hole science forward. To answer them, we're building bigger and better tools. The next generation Event Horizon telescope is getting a serious upgrade. We're adding more telescopes on the ground and even planning to launch some into space. This will give us a much sharper, more sensitive view of black holes. We'll be able to observe them in different colors of light at the same time, helping us understand the swirling disks of gas and powerful magnetic fields around them. But the most mind-blowing part, we're going to make movies of black holes. Real videos showing matter zipping around the event horizon, revealing the chaotic dance that's currently hidden from us. This will let scientists measure black hole spin with incredible accuracy and test Einstein's theories in the most extreme gravity imaginable. We'll be able to image many different black holes, comparing how they feed and how they launch their powerful jets. And then there's LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. This isn't your average telescope. It's a massive gravitational wave detector in space, made of 3 spacecraft flying in a giant triangle formation, with 2.5 million kilometers separating each one. LISA is designed to pick up the low-frequency gravitational waves created when supermassive black holes collide, a cosmic symphony we can't hear from Earth. It will be so sensitive it can detect these monster mergers years before they happen, watching as they spiral closer and closer together. LISA will also hunt for something called extreme mass ratio inspirals, which is when a star-sized object spirals into a supermassive black hole. By tracking this process, we can map the very fabric of space-time around the event horizon with stunning precision. Back on Earth, we're also digging deep. The next generation of gravitational wave detectors will be 10 times more sensitive than what we have now. In Europe, the Einstein telescope will be built underground with 10-kilometer-long arms in a triangular shape. Here in the United States, we're planning Cosmic Explorer with enormous 40-kilometer arms. These incredible machines will be able to detect the mergers of stellar mass black holes from anywhere in the observable universe. We'll be logging thousands of these events every year, creating a detailed census of black holes, charting their masses and spins. This will even allow us to see the very first black holes born from the universe as first stars, giving us vital clues about how they grew and changed over cosmic time. Speaking of the early universe, the James Webb Space Telescope is already changing the game. With its powerful infrared vision, it can peer back in time to see the first galaxies and quasars taking shape. JWST is finding black holes that existed less than 500 million years after the Big Bang, which is forcing scientists to rethink how quickly these giants can grow. We're measuring their mass and how fast they're eating in this cosmic dawn, putting our theories of black hole formation to the ultimate test. Every new discovery pushes the frontiers of our knowledge, showing us just how early these supermassive black holes started shaping the cosmos. Black holes are more than just cosmic vacuum cleaners. They're the perfect laboratories for testing our most fundamental theories of physics, especially quantum gravity. If we could ever detect Hawking radiation, it would be the smoking gun for quantum effects playing out in the warped space-time around a black hole. Some theories even predict gravitational wave echoes, faint signals bouncing off strange quantum structures near the event horizon. Finding these would prove that there's physics beyond Einstein's general relativity. As we watch stars get devoured by supermassive black holes, we'll be able to test if event horizons are perfectly smooth as classical physics predicts, or if they have a fuzzy quantum texture. Theories like string theory and loop quantum gravity are no longer just math on a blackboard. They're making real predictions we can finally start to test. Here's a wild thought. What if the mysterious dark matter that holds our galaxies together is actually made of black holes? Not the giant ones, but primordial black holes, formed in the fiery chaos of the Big Bang's first seconds. We're actively searching for them in a bunch of different ways. We're looking for tiny flickers of light caused by their gravity bending the light from distant stars, a technique called gravitational microlensing. We're listening for the gravitational waves from them crashing together, and we're searching for flashes of gamma rays from the tiniest ones as they evaporate. The Vera Rubin Observatory, in particular, will conduct massive surveys to hunt for these elusive objects. Finding primordial black holes would solve one of the biggest mysteries in cosmology. What is dark matter? While also opening a window into the universe's very first moments. We know about small star-sized black holes and the supermassive giants at the centers of galaxies. But what about the ones in between? These intermediate mass black holes, weighing hundreds to thousands of times the mass of our sun, have been incredibly hard to find. Future X-ray telescopes will systematically scan the sky for super bright objects that could be powered by these missing link black holes. The LISA space mission will also be able to detect the gravitational waves from their mergers, which would finally give us definitive proof that they exist. With better radio and optical telescopes, we'll also search for them hiding in the hearts of smaller dwarf galaxies. Figuring out the story of these middleweights is a crucial step in understanding how supermassive black holes got their start. And the movies are coming. Future observations with the Event Horizon Telescope will create real-time videos of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. We'll be able to watch clouds of superheated gas as they orbit our galaxy's central monster, revealing the turbulent chaos of its accretion disk, what causes its sudden flares, and how it launches powerful jets. By watching in different kinds of light at the same time, from radio to X-rays, we'll get a complete picture of what is happening. Scientists will be able to track individual blobs of plasma as they whip around at nearly the speed of light, just hours before they take the final plunge past the event horizon. As our telescopes get even sharper, we might be able to see something truly spectacular, the photon ring. This isn't just the main ring of light we've already imaged. It's a series of fainter, nested rings created by light that has orbited the black hole multiple times before escaping towards us. These delicate rings are like a fingerprint, encoding precise information about the black hole's mass and spin, and the very shape of space-time right at the edge. Detecting these photon rings would be an incredible test of general relativity, and would give us a view of the closest, most stable orbits possible around a black hole. Ultimately, the goal is to build a complete family tree of black holes. Future observations will map out the entire black hole population across all of cosmic history, their masses, their spins, how often they merge, and how all this changed as the universe grew older. This black hole ecology will show us which ways of forming black holes were most common at different times, how they influenced the growth of their host galaxies, and what really happens when galaxies collide. By combining information from gravitational waves, light, and even mysterious particles called neutrinos, we'll gain a richer, multi-dimensional understanding. We'll finally see black holes not as lonely monsters, but as a deeply interconnected cosmic web that has shaped the universe we live in. And you don't have to be a professional scientist to be part of this incredible journey. Amateur astronomers are already making huge contributions to black hole research. They track the flickering brightness of distant quasars and star systems with black holes, providing constant data that big professional telescopes just don't have the time to collect. There are also citizen science projects where anyone can help analyze gravitational wave data or classify images of galaxies. As our new telescopes produce overwhelming floods of data, these contributions from passionate amateurs will become more important than ever. The future of black hole discovery is a partnership, open to everyone who looks up and wonders. We are truly standing at the dawn of a golden age for black hole astronomy. New telescopes, better theories, and creative new techniques are about to unlock discoveries that will completely reshape our understanding of the cosmos. In the coming decades, we'll answer questions that have puzzled us for a century, and we'll almost certainly stumble upon new mysteries that no one has even thought to ask yet. Black holes, once just an idea in an equation, are now real observable objects, and studying them is pushing physics to its limits, leading us toward a deeper understanding of space-time, matter, and reality itself. Over a century passed between Einstein's equations and our first actual photograph of a black hole. In that time, these cosmic enigmas went from being just quirky math problems to confirmed real objects in our universe. This incredible journey, from a wild theory to a captured image, from widespread disbelief to universal acceptance, is a perfect example of how science, through patience and rigorous thought, uncovers the deepest secrets of nature. Black holes have completely reshaped what we know. They've taught us that space-time isn't static. It can bend, it can ripple, it can even break. They showed us that singularities exist, places where our current physics just stops making sense, pushing us to find a new, grander theory that marries the quantum world with gravity. They revealed that even space-time itself follows the rules of information and thermodynamics, hinting that our reality might be a kind of hologram. They have also shown us how galaxies and their central black holes grow up together in a beautiful, intricate cosmic dance. Every single discovery about black holes has pushed the boundaries of physics, cosmology, and our fundamental understanding of what reality even is. This journey wasn't made by one person, but by generations of brilliant minds. It started with Carl Schwarzschild, who found the first solution to Einstein's equations while in the trenches of World War I. Then came John Wheeler, who gave them their famous name and championed their study when many others were skeptical. Stephen Hawking unveiled their quantum side, showing they aren't entirely black after all. Roger Penrose proved that singularities are an unavoidable consequence of gravity, work that earned him a Nobel Prize. Kip Thorne pioneered the search for gravitational waves, and Reinhard Genzel and Andrea Ghez meticulously tracked stars to prove the existence of Sagittarius A at our galaxy's heart. And we can't forget the Event Horizon Telescope team, 300 scientists across the globe who collaborated to photograph the unseeable. Each one of these pioneers added a crucial piece to the puzzle. Of course, none of this would have been possible without technology. Early radio telescopes gave us our first glimpse of quasars, powered by monstrous black holes. X-ray satellites let us see the glow of matter spiraling into their stellar mass cousins. Infrared telescopes pierced through cosmic dust, allowing us to watch stars orbit the black hole in our own galaxy. Gravitational wave detectors like LIGO and Virgo felt the faint tremors in space-time itself, ripples smaller than an atom's nucleus. And the Event Horizon Telescope created a virtual telescope the size of our entire planet. Each new piece of tech opened a new window on the universe, and the discoveries of tomorrow are waiting for technologies we haven't even dreamed up yet. Black holes don't just challenge our science, they challenge our philosophy. If a black hole destroys information, does the past truly vanish? If time literally stops at the event horizon, what does that mean for cause and effect? Could our entire universe exist inside a black hole in another, larger cosmos? These questions push us to the very edge of what we can know and what truly exists. Black holes force us to confront the limits of human understanding, blurring the line between physics and the deepest questions of our existence. It's no surprise that few things in science capture the public's imagination quite like black holes. They're stars in movies, they inspire music and art, and they become a powerful metaphor in our language. That first black hole photo was front-page news worldwide. Stephen Hawking's books on the topic became global bestsellers. This isn't just a fleeting interest. It taps into our deep-seated human curiosity about the extremes of nature and the ultimate boundaries of reality. Black holes show us that the universe is far stranger and more magnificent than our everyday lives suggest, fueling the awe and wonder that drive science forward. At their core, black holes represent the ultimate quest in physics, the search for a single theory that can unite quantum mechanics and general relativity. At a singularity, both theories must apply, but they are fundamentally incompatible. One describes the tiny world of particles, the other the grand scale of spacetime. They use different math, different assumptions, different languages. Theories like string theory and loop quantum gravity are our best attempts to bridge this gap. Black holes are the testing ground. They won't let physics rest until it finds a complete, consistent description of reality. And make no mistake, black holes aren't just strange oddities. They are essential to the cosmos. They are the architects of galaxies, regulating star formation and shaping the large-scale structure of the universe. They stir and redistribute matter and energy over billions of light years. The universe as we see it today, its galaxies, its web-like structure, maybe even its ability to host life, is a direct result of the influence of black holes throughout cosmic history. To understand the universe, we absolutely must understand black holes. Despite all we've learned, the list of what we don't know is just as long. What really happens inside a singularity? How did supermassive black holes get so big so fast? Do middleweight black holes exist in large numbers? Can we ever detect Hawking radiation? Are there primordial black holes left over from the Big Bang? Does information truly escape? Each answer we find just opens up a new set of even deeper questions. That's the beauty of science. Black holes guarantee that for centuries to come, there will be fascinating work to do and discoveries that will undoubtedly blow our minds. This grand cosmic drama inspires new generations to dive into physics, astronomy, and math. Young people drawn in by the mystery of black holes discover the elegance of relativity and the deep satisfaction of solving nature's puzzles. The students of today will build the observatories of tomorrow, develop the theories of the future, and make discoveries we can't yet conceive of. Black holes ensure that the frontier of science remains exciting and relevant, attracting the brightest minds to ask the most fundamental questions. The story of black holes is a story of humanity at its very best. It's a tale of international collaboration, of patience that spans generations, and of a pure dedication to truth. Scientists from dozens of countries share data, credit, and the thrill of discovery. This sustained collective commitment to understanding the universe for its own sake represents one of the highest aspirations of our civilization. And this story is far from over. New space-based observatories like LISA are on the horizon. Even more powerful ground-based telescopes are being built. The next generation Event Horizon telescope aims to create actual movies of black holes. New discoveries await, new theories will be tested. Einstein could never have imagined we'd one day take a picture of his mathematical curiosity, yet here we are. The golden age of black hole astronomy has only just begun. So black holes, places where space-time bends to infinity, where time itself halts and from which not even light can escape. We have journeyed from abstract equations to gravitational whispers to actual photographs, transforming these cosmic monsters from myth into reality. They challenge our every notion of space, time, and information. They sculpt galaxies and maybe even give birth to new universes. They represent both the vastness of our knowledge and the infinite ocean of what we still have left to learn. They are a constant, humbling reminder that we live in a universe more beautiful, more profound and stranger than we ever dared to imagine. And our journey to understand it all has only just begun. If you enjoyed this journey into the unknown, don't forget to like, subscribe, and hit that notification bell so you won't miss our next adventure into the cosmos.